Thank you, Prince. Hi, I'm Hyojin, and I'll walk you through our privacy research driven by Project Aria with my colleague Vincent. AR devices are the most personal devices that people can take with them wherever they go. Privacy for machine perception in AR, on the other hand, is a relatively a new field of study, which is at the intersection of many other fields from vision, ML, hardware, sensors, systems, to policy. While many researchers recognize that privacy is an important problem to address in vision systems, it still remains abstract and it's not clear where to start such research. This is where Project Aria comes in. While there can be myriads of hypothetical privacy challenges in AR, Project Aria can help us identify a constrained set of practical challenges among them. Researchers can then preempt these challenges and concretize the research paths to address them. Now, from a computer vision perspective, what kinds of problems can we concretize? Here are some examples. Visual localization systems need visual sensor inputs, which may contain private information. So we want to ensure that data and compute is secure to prevent attacks such as home doxing from raw or derived data. For example, researchers have shown that it is possible to invert visual descriptors to synthesize input images. And with the recent advances in deep learning, the quality of the reconstructed images has been significantly improved. Second is prohibiting the degradation of the system, such as malicious attackers contaminating the crowdsource map to cause localization failures or breach map integrity. There are also fundamental questions that are not answered yet. For example, how do we even measure privacy to compare if a localization system A is better than B? In the remainder of this talk, we'll introduce some of the case studies focused around preventing descriptor inversion attacks and access controls for 3D point cloud maps. And our first step is to analyze visual descriptor inversion attacks. In this scenario, the descriptors are extracted from the client device and sent to the service provider. The service provider then performs localization and sends back the post of the device back to the client. While the visual descriptors are not human readable, it is possible to estimate the input image using the techniques that we saw earlier. While the practicality of this attack is still somewhat theoretical, it provides an example of how to concretize an abstract research challenge in this space. One of the key takeaways from our analysis is the utility and privacy trade-off for visual descriptors. In this figure, we show descriptor inversion results with varying number of key points, where the red dots indicate the key point locations. Privacy was quantitatively measured by the structural similarity index to the original image, and the utility was measured by the matching accuracy. As we decreased the number of features, we were able to achieve better privacy metric but lower utility scores. Furthermore, when comparing different types of descriptors, the better the descriptors are for image matching, the easier it is to invert them. And now we present a solution to this problem using adversarial learning. Ideally, we want a descriptor that does not reveal the image content without a compromise in its performance. However, these are two competing objectives because of the trade-off between privacy and utility as we saw earlier. In this work, we directly minimize this trade-off by using an adversarial approach to train visual descriptors. We let a feature encoding network and image reconstruction network to compete with each other such that feature encoder tries to prevent the image reconstruction with the generated descriptors, while the reconstructor tries to recover the input image from the descriptors. Specifically, we introduce a small feature encoder network, NinjaNet, that can be trained with any existing visual descriptors and transform them to our privacy-preserving descriptors, NinjaDesk. In addition to the traditional metric learning loss, such as triplet loss or second-order regularization, Our feature encoding network is also optimized with an adversarial loss for image reconstruction. For the adversarial loss, we jointly train an image reconstruction network, aka descriptor inversion network, to reveal the original image content from the descriptors. In this way, our NinjaNet learns to hinder the image reconstruction while being optimized for the correspondence matching. The scalar parameter lambda controls how much we prioritize privacy over utility. And I'll show you the results in the next slides. From left to right, we show original input image, descriptor inversion results on SOSNet, and our NinjaDesk with different privacy parameter lambda. The higher the lambda is, the more aggressive NinjaDesk tries to deteriorate reconstruction quality by the inversion model. We further show qualitative results on human faces using the deepfake detection challenge dataset. Similar to what we observed in the landmark images, we see progressing concealment of facial features as we decrease lambda. On the H-patches benchmarks, NinjaDesk is comparable with the SOSNet, which is shown on the bottom, across all three tasks, including patch verification, image matching, and patch retrieval. When compared with the state-of-the-art sub-hybrid lifting method, which is shown in red, our NinjaDesk, which is shown in blue, significantly outperforms the sub-hybrid lifting method for both hardnet and SIP descriptors. Here we show more qualitative results using a pair of matching images for three different types of base descriptors: SOSNet, hardnet, and SIP. And I would like to now change gears to discuss verifiable access control on 3D point cloud maps. Access control is a well-known concept that has a long history. It tries to decide if a user can perform certain actions on objects or resource. In our physical world, we have invented security guards, turnstiles with card access, and etc. The permissions of Linux files is another well-known example of access control. The goal of this work is to develop a formally verified interface for access control on 3D point cloud maps. We want to ensure that users are not able to map a private space or read any existing map points in the space without appropriate permissions. The access control system takes a user's request to access a point in 3D space and evaluates the access request based on the internal knowledge of the spaces and the access policies, then gives permission or denies access based on the formal reasoning based on SMT. SMT stands for Satisfiability Modulo Series, and it is used to prove correctness of safety-critical systems like flight collision avoidance. When the access is granted, the map points then can be read or written for mapping and localization. This is an example of our access policy interface. Each policy entry contains name of the policy, effect, such as allow or disallow, principal/user, and actions such as read, write, or localize, and space and conditions. As you can see, the interface is reasonably easy to write and modify for the users so they can take full control of their access policies. And access to each space is granted only if there's an allow policy and there does not exist a deny policy. And each access policy is then encoded in SMT formula for formal verifications through SMT solver. Here we show some examples of our access control access control on point clouds in action. The policy we wrote allows the user to access the common area on the second floor of the second level of the house and the guest room. On the left, you see the user's view in area glasses and his current location, which is shown in yellow dot on the right, on top of the space segmentation results. You can see that access to the 3D points in the common area were granted access by the system and are shown in their average color. while the access to the points in the bedroom on the left are denied by the system, actually the master bedroom, are denied by the system and are depicted in red crosses. And before I conclude the talk, I wanted to illustrate the interdisciplinary nature of privacy and security challenges for machine perception in AR. Suppose we have a privacy policy, such as only allow guests to map the shopping mall during business hours. There are a number of issues that we need to solve. For instance, what does this policy mean for access control and actual system enforcement mechanisms? And how do you prove that what you built is correct? And how do you know that it's reliably correct? And how do you know what data assets this applies to? The specifics matter because when we build actual systems, we need to be precise and not abstract. At a higher level, this example highlights the challenge with the human-readable policy. While human-readable policy is how we reason about privacy, it's not how system implementation reasons about privacy. In order to enforce them, we have to build a systematic translation between human-readable policy and machine perception system implementations. The key challenge with this is that it requires many disciplines to get it right. Privacy policy experts should define human-readable policy inputs. Security experts should provide the toolbox of enforcement mechanisms. And vision and machine learning experts like you should define what data is needed and what is stored and how they're processed. Finally, the languages and verification experts should translate this policy across these abstraction boundaries to enforce access over data and prove correctness. In conclusion, we know that there are privacy challenges for machine perception for AR, but they are abstract. While Project Aria is not a product, it is built to help concretizing the practical privacy challenges related to the always-on egocentric data. And we need experts across the fields to come together to define and solve privacy challenges such that we can maximize the benefits of AR that everyone can enjoy. So please reach out to us for Aria. They're available. And I'll now take questions.
Hello, yeah,
Hi.
great talk. One thing I wanted to ask, like in the Ninja Desk paper, right? You use SSIM as a privacy metric. So that basically says that if you can reconstruct image, similar looking image as the ground truth or not, right? Let's say I'm able to like train a classifier on like a face recognition network on it, right? And if that face recognition network can tell if the person is there or not, like if you are in the image or not, based on like that amount of obfuscation, right? Is SIM a good metric to measure, or is like downstream vision tasks, which are like obviously much more powerful than human vision would see as like some data, Okay, so that's the question basically.
Right. So one of the fundamental research topic that we brainstorm is the metric for privacy.
Yeah.
So it is obviously like application dependent. So it's kind of hard to say this one is the right metric. And I think there should be like theoretical work, maybe from coming from differential privacy perspectives, or using this formal verification and stuff. But yes, but that's still an open question. And currently in this work, we wanted to measure whether this image reconstruction network can reconstruct the original image from the descriptor. So that's why we use this SSIM for the metric. Yeah.
I have another question.
Yeah, sure.
So if you look at basically how an image is captured, so your main privacy concern is basically visual, right? Everything else is fine, like I'm you or whatever, who cares? So you're capturing using a lens, basically, right? So you have first, when the data capture happens, it's the optical domain, right? Then it happens in the analog domain, and then you have the digital domain. So once the data is in the digital domain, it's already like accessible to anyone.
Data is in where?
In the digital domain. When you capture the
Digital
image,
domain?
like, so when you have converted from the analog circuit to some digital value, right, some bits, so that data is available for everyone to like, anyone to like who, if the camera is connected to the internet, like that data is like, can be streamed like easily. That has been shown previously. Is like their work in like Meta, where they're looking at into filtering out information before in the optical domain or in the analog domain, because like let's say some
in sensors, you mean?
Yeah, in like the camera basically.
Yeah.
Designing a camera basically,
Yes.
not like a normal camera, right? And thinking about improving those utility functions that you have, let's say object detection or something, or let's say pose estimation, but trying to like keep some privacy aspects, like reconstruction you can't do, but you can do pose estimation, or you can tell camera's ego motion, but you can't really tell like what the scene is, right?
Yes. So our sensors team is also looking into this. So there are works. So
Okay.
if you want to join our internship, then you can work on those projects.
Okay. Well, I'll talk to you later then.
Oh, okay.
Yeah, okay.
Yeah,
Thanks a lot.
sure.
Thank you, Hojin.